This video brought to you by Mtron. So logarithms have lots of applications in many fields, especially with translating variables between two very different scales, meaning one super large and one really small. Scientists often use what's called log plots, so they graph log on one variable in order to compress its scale. In my grad stats classes, we can transform the variables by taking log of them if we want to try to see if it's normally distributed, etc., etc. So here's an example from chemistry. Those of you that are in chemistry, you will know far more about this than me. But these are the acidic acid titrations. Here's the number of H positive ions, I believe, and this is the saturation percentage, whatever that is, and this is pK equal to 4.90. No idea what that is. Someone could tell me, I'm sure. Notice this is not a log scale. These numbers are really small, 1 times 10 to the negative 7. And then when we do the pH formula to these positive hydrogen ions, we get a formula that does negative log of H plus, and the scale looks nice and pretty, right? You got these nice whole number values, 76543. So using this left side graph, we can see that a 45% saturation, boy, where is that? What is this? 1, 2, 3, 4, what? 1, 2, 3, 4. Okay, that's 5% each, so this would be 45. There it is. A 4.5% saturation, the concentration of hydrogen ions, positive hydrogen ions, is 1 times 10 to the negative 5. What value of pH does that correspond to on the right side graph? So that would be a 5.0, positive 5.0. So then below the right side graph, you see how chemists define pH as an equation. So using that, what is the hydrogen concentration of acid with a pH of 5.25? Well, here we're going to say 5.25 equals negative log of the number of hydrogen positive ions, which I might just call X, and then we're going to solve for that. So let's divide both sides by -1. So we get this. Then I know, using what I know about logarithms, the base here is 10. So we're going to say 10 to the negative 5.25 power equals X. And that would give us a number for the positive hydrogen ions, which I'm going to have to use Desmos to do. To do that, here goes Desmos, and we're doing 10 to the negative 5.25, and we get, ooh, that's an awful number. X is approximately equal to 0.00000563. No, I feel like that's totally wrong. Hang on, I gotta figure this. Okay, no, I was totally right. It just didn't feel right. Note here in Desmos, I typed in y equals negative log x, and then I put in 5.25, and I noted their intersection, and there it is. I guess I should trust what I'm doing here, right? Okay, so how did using the pH make the graph simpler? Well, the x-axis values are now integers. Let's say whole numbers. Okay, so let's look at one last example here, and we'll be done with 5.3. So example 6 it's kind of an interesting thing. Based on repeated observations, we can find some amazing patterns that shows the very nature of cities as alive. There's a link down here where you can check out where this came from. So this psychologist Mark and Helen Bornstein, back in 1976, looked at the average walking speed of people living in cities of various populations, and they found that this would model how fast people walked. Interesting. So notice he's using a natural log in it, and the population of New York City is currently this. How fast on average does the model predict that people walk in New York City? Well, this is just kind of your basic plug and chug thing into the model. I always argue that the most interesting thing would be where did this model come from? Now, we have to be careful. Note that P is in thousands. So 8.37 million is 8,337 thousands. So I had to convert that 8.37 into a value that made sense. All right, let's smash this in Desmos, and we'll get that average walking speed. 0.37, natural log of 8,337 plus 0.05. They walk, on average, 3.39 feet per second based on our units. All right, so let's describe the shape of the graph of the Bornstein model. Well, instead of describing it, well, let's graph it to make that description, all right? I'm just going to get us a brand new graph, and here goes. 0.37 natural log of x plus 0.05. So a nice description of this, here it is. Notice the larger a city gets, obviously the faster people walk, but it's not a super fast growth in terms of walking. So what this tells us is that as the population increases, the walking speed increases, but slowly. So let's at least write that down, huh? As the population increases, the walking speed increases. Now, obviously, at some point, if you're walking super, super fast, you're no longer walking. I don't know if you've ever seen those speed walking championships. People look really funny, but there's some definition of how to walk. I think like your knees can't bend or something, or your both feet have to, one foot has to be touching the ground at a time or something. I don't know. Okay, so we do some observational and statistical number crunching. Researchers found the average walking speed in Lansing, Michigan to be approximately 0.55 meters per second. Oops, we immediately have a problem because our model is in feet per second. So let's estimate the population of Lansing based on the information, and then we'll verify it. Well, 0.55 meters per second. We need a conversion factor, and we need to know how many meters are in a foot, and we're going to write it in this manner. And boy, I don't know that offhand, so we go straight to Google and say feet to, actually we want meters to feet. And so the conversion factor is 1 meter equals 3.28 feet. And instead of using that, I'm going to do my conversion factor that I was going to do, 0.55 times 3.28. That gets us 1.804. So 1.804 feet per second is how fast folks in Lansing walk. So we're going to plug this into our equation, and that is 1.804 equals 0.37 times natural log of x plus 0.05, and we're going to solve this for x. Let's do a graphical solution just for fun. So I'm going to graph these two sides. We're going to use the intersect method. And I chose this because I already have the equation typed in, right? So I'm being efficient with my time. This is the equation here. All we have to do is find where these two lines intersect. So I'm going to zoom way out and then zoom in a little bit. There it is. 114.496. I'm going to go ahead and draw this. 114.496. So here's me showing my work. I know it's not the greatest work in the world, but it suffices. And note that this is in thousands, so we're claiming that Lansing has a population of 114,496 people. We are supposed to Google check that and make sure that is legit. So let's quick Google population of Lansing, Michigan. And it says 116,986. Not bad, right? Not bad.